Today I would like to talk about some of the works on the epidemic models. I would like to introduce several models of epidemics and several things that people know about them. And this is based on several joint works with Alan Sly and Bamidi, Nam, Hara, and a couple of my students. So let me first start with introducing a couple of epidemics models. So today we will talk about three variations, SIR, SIS, and SIRS. So here S is for susceptible, I is for infected, and R is recovered or removed. Okay, so it means that so we have a network of individuals, there are connection between them, and an individual can be, susceptible or healthy, and they can get infected from, people who are currently infected, and after some time they become, recovered from the disease. And for the SIR model, when you recover, you are removed from the network, meaning you are not going to contract the disease or spread the disease further. So that's the SIR. SIS is, so you are susceptible, you get infected, and after some time you recover, become immediately susceptible again. SIRS is somewhere in between, so you are susceptible, infected by some of your neighbors, and then become removed or recovered at some time, and there's some period of immunization period where you are, immune from the disease, and after that period you're susceptible again. As for the notation, we'll have lambda being the infection rate, and we have recovery rate, what we fixed to be 1. And alpha, what is the deimmunization rate. And all the clocks are going to be exponential clocks. And so for here is an example. We have a star graph. That means we have a vertex, which we call the root, and a bunch of neighbors. So let's say we have n neighbors. This we call it an n graph. And let's say row is initially infected. And all the leaves are susceptible. So then for each of them, so firstly we'll have a recovery clock at row. So that is going to be an exponential with the rate being recovery rate. And for each of the leaf here, we sample an exponential clock of rate lambda, that's the infection rate. That stands for the time it takes for row to infect the corresponding leaf. And each of them are independent. So each of the leaf have an independent exponential lambda, and whatever clock that happens before the exponential 1 clock, that leaf will get infected. Okay, so does it make sense, the models? And the question of interest would be, is there a phase transition? How does that, what is the values of the parameters at the phase transition? How long does it take for the process to be, to terminate? For all of these processes, it terminates when there's nobody infected anymore. So either everyone, meaning after some time, everybody will be susceptible or recovered. And if there's nobody infected, then there's no more changes to the network. And we call that the survival time. So tau survival time. It means the time it takes for, everybody to, so first time where no more I in the network. Okay, so let's start with our, simple looking kind of graph, and maybe think about, what is the value of tau as we vary the parameters. Probably here the easiest model in this case, in this particular case, is SIR. So if you have the root infected, what happened in SIR? So before this exponential 1 clock, the root will infect some of the leaves. So for instance, it will infect these two and not infect the rest, for instance. And so what happened next is the process will wait for these guys to recover, and that's it. That's the end of the process. Now, this is an exponential 1 clock. So typically the root recover in time 1. During that 1 time, it infects typically lambda n leaves. And the time it takes to wait for them to recover is the maximum. So it's going to be the maximum of a bunch of x1, x of lambda n. These are IID exponential lambda. Okay, and we know that this maximum is of order log of lambda n. So survival time is going to be, the time it takes for the root to recover plus the time it takes for the infected leaves to recover. So that's would be what happened for the SIR. Now what about SIS? So we have the root infected, or in fact, lambda n leaves, and then the root will recover. Now what happens to the leaves is that these infected leaves, they're going to try to reinfect the root. And once the root is infected, it will try to infect more leaves and so on. Okay, so what is the chance that all of these lambda n leaves fail to reinfect the root? The chance that, let's say this guy is infected, it will reinfect the root with an exponential lambda clock, right? And it will recover with an exponential 1 clock. Now the probability that this exponential, so let's say this is x, and this is y, the probability that x is bigger than y. So this is fail to reinfect the root. The probability that this vertex fail to reinfect the root is the same as the probability that it recover.
That's x less.
Yes, thank you. So the probability that it will recover before sending the infection to the root. And that happens with probability 1 over 1 plus lambda. So the probability that all of them fail, so probability of all infected leaves fail, is 1 over 1 plus lambda to the power lambda n. So this is about 1 minus, we are thinking about lambda being small here. So this is e to the minus lambda squared n. So, and so it would mean that, let's think about like the process happening in several rounds. Each round starts at the root being infected, and it ends when the root is reinfected again after recovery. So a round fail with this probability, so we would expect that, we would expect to see about e to the, some constant lambda squared n successful rounds before you see a failed round. And therefore, the survival time is, for the SIS, is exponential, is e to the lambda squared n. Now, the intermediate one is SIRS. And in SIRS turned out to be more complicated than the other two models, and we barely know anything as far as I'm aware about the SIRS. There is a conjecture by Ferreira et al. In 2016 who conjecture and do some heuristic argument and show that, okay, the survival time is going to be of order lambda square n to the power alpha, where alpha is the deimmunization rate. And it was proved, so this conjecture. So this is on physical reviews, they come up with some heuristic. Friedrich et al. In 2022 show that the survival time is smaller than n to the power alpha log n for any value of lambda. And let me explain some reason why we have, in contrast to this one, we have an exponential survival time. Here is a polynomial survival time. And the reason being that, so we start around with the root being infected, right? And it will infect about lambda n leaves. Now, what is the chance that this guy failed to reinfect the root? So, firstly, the root is infected, and then it will recover during an exponential time 1. It stays immune during an exponential alpha time, and then becomes susceptible again. Now, during this time, this guy will try to recover. And then when the root is susceptible again, the ones that remain infected, they will try to reinfect the root. So let's say for simplicity of our heuristic, let's say this is also alpha equals 1. Okay, so assume, so at the time that the root recover, it already successfully infect about lambda n leaves. Now what is the, so each of them recover with rate also during time exponential 1. And the root also takes time exponential 1 to become susceptible again. Maybe I can draw here. So this is when the root is infected. It will take time exponential 1 to recover. And then take time exponential alpha, which we suppose that is 1 for the heuristic, to become susceptible again, and then it's infected again with exponential, so here we have about lambda n infected leaves. And each of them recover with a rate an exponential 1 again. Okay, so how many so during the time that the root is immune, these leaves, some of them recover, and how many are remain here? So let's say we have B leaves remain infected. Now, what is the chance that we have B leaves infected? Any guess?
Binomial formula.
So we have, and that's the reason why I suppose alpha equals 1 for, this heuristic. So this is an exponential, let's call it x0. That's exponential 1 clock for them, for the root to be, d-immune. And each of them, we have an x1 up to x lambda n. And we have b leaves remain infected. I mean, if we rearrange them, x1 smaller than x2 smaller than x lambda n, and we have b leaves remain infected if, this is x0. This is the position of x0. There are b many here. And because each of them is just exponential 1, the probability would be, x0 could be equally anywhere here. So the probability is just 1 over lambda n, I guess. Okay, so the probability that the round fails is the sum over b. Probability that we see b remains remain infected. And the probability that they all fail to reinfect the root, which similar to the SIS, is 1 plus lambda to the power b. And so it is the same as 1 over lambda n, the sum over b, 1 over 1 plus lambda to the power b. So, and b is from 0 to lambda n, but we can suppose that that's the sum to infinity. And so that's 1 over lambda n, 1 divided by 1 minus 1 over 1 plus lambda. So 1 over lambda n, and then we have lambda over 1 plus lambda, which we can suppose that is 1 because we think about lambda as being small. No. Yep, thank you. So 1 plus lambda, which we can think about it as 1, and then there's a lambda here. So we get 1 over lambda square n. So each round fail with probability 1 over lambda square n. So therefore, we expect to see lambda square n rounds successful. And therefore, we would expect SIRS to survive until time lambda square n. That's for alpha equals 1 in general. We do that. We can try to do the same calculation as y and get the where that heuristic, this conjecture comes from, and this is basically how the idea of proving this one with my students.
Can I ask a question?
Yes, please.
Why are you taking this particular star graph?
That's a great question. Star graph, and I'll talk more about that later for other complicated graph. Star graph is the building block, So when we look at a random graph or a big graph, and the process, we want to see, how long the process survives. Let's say we start with one individual vertex infected, right? That vertex will, may have a chance to infect a high degree vertex. And that high degree vertex, if it survives, if the process in that neighborhood of that high degree vertex survive for a longer time, that will allow the process to go, infect another high degree vertex. And that will, explain why the process on the graph survive for a long time. If the infection rate lambda is small enough that the process cannot go from one high degree vertex to another high degree vertex, and the process die out quickly. And so studying the epidemics on like hub or like large star graph is a good starting point. So with my students, and this is my graduate student, my high school student, we show that the conjecture is true. And so we get rid of the log and we prove a matching upper and lower bound. That is lambda squared to the power alpha. Now that is the story for star graph. I want to talk a little bit about deterministic large graph, and then I want to move on to talk about random graphs. So here is some very general bound, deterministic large graph, or just any graph. What do we know about epidemics on if I give you a deterministic graph, is there anything that we can say about the processes? Now, there are some phase transitions that are of interest. Firstly, so we think about the graph G as finite graph for now. You have a finite graph G, and on top of that we have an epidemic process. Now, if lambda is smaller than some lambda c, the process survives for a short time. And what does it mean to be a short time? It depends on the different, whether we're talking about SIS, SIR, or SIRS. And if lambda is larger than lambda c, then the process survives for a long time. And we want to understand, okay, what is the value of lambda c? So drive, I'm sorry. In 28, show that, yeah, sorry, I also got the wrong thing that I want to say. 2006. Show that if lambda, so for the SIS, if lambda is smaller than lambda 1a, where A is the efficiency matrix, of G, and lambda 1a is the largest eigenvalue of A. Okay, so if lambda is smaller than lambda 1a, then the process survives for a short time for any graph. And if lambda is larger than the isoperimetric constant, then the process survives for a long time. And this isoperimetric constant, I'm sorry, this 1 over eta, where eta is the isoperimetric constant and defined by minimum number of edges between a subgraph and the complement over the size of the subgraph. Sorry. Okay. So here, basically, the idea here is explain, what we typically expect. So what does it take for a graph to survive for, what happens when the process survives for a long time? So let's say here, at some time you have S being the, I'm changing it to a different notation to not confuse with the susceptible one. So A, E, A, no. What did you say? U, thank you. U, and U. Hold on. So let's say at some time you have the set of U being the set of vertices being infected. And these are the edges going out from U. Now, if if U has a lot of neighbors, there's some expander property. So if U has a lot of neighbors, then it can infect a lot of neighbors in the next time interval. And so that's, if this happens, if lambda is large enough, then this allows, the process to go, expand very big in the graph and survive for a long time.
By loss survival, you mean exponential in the size of the graph?
For SIS, yes. That's a great question. So for SIS, survives for a long time means that it survives for an exponential time. Exponential n, where n is the size of the graph.
And short time means what?
Short time for the SIS means it survives for a polynomial time.
In the size of the graph.
Yeah.
And the constants that are hidden in that depend only on like the degree and like these spectral properties or something. Like, should I imagine there's a sequence of graphs and then there's a constant that only depends on lambda 1 and nice and parametric?
I would say the constant is you mean if lambda is smaller than 1 over lambda 1a, for instance, and there's a...
Then there's a universal constant such that for all graphs on n vertices with that, the survival times at most n to the c. Log n, whatever it is.
Yes.
I would think so. Yes.
Right, because the adjacency matrix already has all the information about the graph and the degree and so on.
Yeah. Yes, and well, one may wonder now. So what about SIR and SIRS? Would one expect to? Now, what happens if lambda is smaller than 1 over lambda 1a? Does the process survive for a short time? Yes, it does, because the process on SIS survives for longest time among the three, because these are have a deimmunization period, and so these survive for a short time. Trivially coming from the SIS, but is it? But then the question is, then is it this one the right thing to look at for general matrices? Of course not, because for SIS, it's natural to look at the adjacency matrix, because whenever you have a vertex infected, it can infect the neighbors. So A, the adjacency matrix A, is the right matrix to look at. But for these guys, there's, if the vertex U is infected, it sends the infection to a vertex V. Let's say SIR, for instance, then we don't care about whether V reinfect U, because after U is infected, it will be removed. So we don't care about reinfection. So A is actually not the right matrix to look at when it comes to SIR. And SIRS, the right matrix to look at least for the SIR, is called the so-called, well, I'm not sure if that's the right matrix, but the more logical one to look at is the non-backtracking matrix, where it looks at the edges coming out of V that does not count this edge. So B is the non-backtracking matrix. So with Solvik Hara and my student Wang, we show that this is true for SIR. So if lambda is smaller than 1 over lambda 1b, where b is the non-backtracking matrix, the SIR survives for a short term. We don't know what is the, a logical matrix to look at for the SIRS. I would tend to think that it's something that is, between the non-backtracking matrix and the adjacency matrix, but we don't know how to do that yet. So anyway, so what I want to say is when you don't have, when you just have any deterministic graph, then we don't know a lot about where the transition happened. Now let's move on to something that we know more. So that go back to the SIS because again for SIR and SIRS we barely know anything. So firstly for the lattice, ZD Harris in 1974 show that, so if the origin is initially infected, Harris show that there exists something, threshold, lambda d, such that if lambda is smaller than lambda d, then the process dies out almost surely. If lambda is larger than lambda d, then the process goes on forever. With high probability, with positive probability. In the case that lambda equals lambda d, it also falls into this case and was proved by Bezu-Heintu and Grimet in 1990. So that's the story for lattice. The next natural kind of structure graph is regular trees. So for regular trees, TD, meaning everybody has degree D. So this one has D neighbors, this guy has D minus 1. Pimentel, in a very classical paper in 1992, show that there are, assume that the root is initially infected. There are 3 phases. If lambda is smaller than lambda 1b, then this is in the extinction phase. And it means that the process dies out almost surely. Lambda is larger than lambda 1d, but is smaller than lambda 2d. Then it's in the weak survival phase. And what it means is the process, there is a positive probability that the process survives forever, but the ones that are infected are further away from the root. The root only get infected finitely many times. And if lambda is larger than lambda 2D, this is the strong survival phase. That means with positive probability, the root keep getting infected infinitely many times. And Pimentel showed that lambda 1 is about 1 over D, and lambda 2 is about 1 over root D, as D goes to infinity.
So there's no exact value, no, per lambda 1, or is it? You said about 1 over D. It's not an exact value, no, for lambda 1 and lambda 2?
We know that it's asymptotically 1 over D, so meaning 1 over D is the...
D is larger.
Yes, but
if D is 3, you don't know exact value.
no,
Okay.
I don't think so. That's a great question. Beyond what is next after regular trees? Regular graphs. Yeah. So GND, this is the random regular graphs where every vertex has degree D. And so what happened? So we have a graph with n vertices. Everybody has degree D. We know the local weak limit of the graph is going to be the regular tree. And let's say we have vertices initially infected on the graph. What do we expect? So is it that lambda, lambda 1 or lambda 2, the ones that tell you whether the process survives, the SIS process survives for a long or short time. So turn out to be lambda 1. That is the, so this is the same lambda 1 over there. And even if you have all vertices infected initially, the infection dies out in time log n with high probability. And if lambda is larger than lambda 1D, even if you have one vertex infected, one random vertex, infected initially, tau is e to the Cn with positive probability. And the proof goes, along the line of passing to the local weak limit and trying to use the, what we know about the regular trees. Now after random, regular graphs, regular tree, the next natural topic is Gauss-Watson tree. With offspring distribution mu. So you have a degree distribution mu, and everybody has the same distribution, all independent. So we have a Gauss-Watson tree. What is, do we have phase transition, and where do they occur? So concerning this, Huang and Durad in 2018 show that if mu has sub-exponential, so does not have an exponential tail, what that means is expectation e to the CD is infinity if D is distributed according to mu. And if this is infinity for every C greater than 0, and we say that it does not have an exponential tail, in that case, no matter how lambda, so lambda 2 is 0, meaning no matter how small you make the infection rate, the process survives for a longer time, the root keep being infected infinitely many times, no matter how small the lambda is. And the reason is being that when mu does not have an exponential tail, for instance, mu is the power law, for instance, that allows to have a lot of high degree vortices. And these high degree vortices keep the process alive for a very long time.
Question. The tree is quenched and it's conditioned to survive, is that?
Yes. Yeah. Great question. Yes. And then direct conjecture that, if mu has an exponential tail, for instance, like Poisson, then lambda 2 is greater than 0. And with Alan Sly, Hamidi, Nam, Sly, and myself, in 2021, we show that that is true. So if mu has an exponential tail, and that means there is just a constant c such that expectation e to the cd is finite, where d is distributed according to mu, then lambda 1 is larger than 0. It means that if you take lambda to be sufficiently small, the process dies out. Do I have like 5 minutes? I will try to think of what I want to do in 5 minutes. There are more stories to continue from here, meaning from here we can pass, from the Gauss-Watson tree to the graph, for instance, to a deterministic random graph or the configuration model. Building on this result, and we know the survival time of the SIS process on the on a deterministic random graphs, for instance. But I want to explain, how to get this kind of result, and this is one of the new tools that we introduced. So if you have a tree, starting with the root, we try to get a recursion bound going, if the survival time of each of the subtree, how can we say about the survival time of the root? The big problem is that there is no, independence between the subtree, because if, let's say, you have this, some vertices here, in fact, that they could, and all of them are healthy here, there is a chance that this guy, reinfect the root, and then the root send infection to these guys. So the survival time of, on the trees are, dependent on one another. So we introduced the new process where we add a grandparent here that is always infected. So, adding the grandparent, when lambda is small enough, when lambda is sufficiently small, then it would, the excursion time of the process, meaning when the root is infected until everything recover, is more or less the same as the survival time of the process. But adding the grandparent here allows us to, make these things independent. And so that allows us to derive recursion bound, to get from the subtree to the big tree. And that's, one of the main tools for us to prove this kind of result. And going back to what Richard asked at the very beginning, why do we study star graph? So for Eder-Shreni random graphs, for instance, when lambda is small, meaning lambda is smaller than lambda d, the phase, then what is the survival time? We show that the survival time is going to be n to the power lambda squared plus little of 1. And the reason being that in Eder-Shreni random graphs, we can find a chain of high degree vertices. And the degree of this is about lambda to the minus 2, each of them, at least. And so the process on each of the stars survive for like a large time. And there are, log n, this, some lambda here. Constant depending on lambda. Okay, and there are many of them, and each of them survives for a constant time. The process on this chain survives for a e to the power cl, where L is the length of the chain, and that turned out to be the one that explained the survival time of the SIS on Eder-Shreni random graphs. So to end the discussion, I want to say there are much more that we don't know about even SIS, and we barely know anything about SIR, SIRS. I think it's a very interesting topic to study. Thank you so much, everybody, for your attention.